Welcome to this first lecture over chapters 1 and 2 in your Pharmacy Calculations textbook. The good news is this lecture is essentially a review of many of the fundamental math skills that you already have. But it'll be important to make sure that you review those skills and are up to date and have practiced those so that we can go forward and be confident in your ability to use your calculator to set up kind of proportions and use dimensional analysis to solve the more complicated calculations that we'll be performing in later chapters. So with that, let's get started. An overall summary for this course is simply to give you an introduction to the type of calculations that you'll be performing as you read and interpret prescriptions and to help determine drug dosages. Now, we want to be able to perform these calculations correctly, time after time, because in the real world, if you make a mistake with these calculations, it could create a medication error that could lead to patient injury, and we certainly don't want that to happen. So this course goes beyond just understanding to a practice, a repeatability without errors that is just critical in the real world application for these types of questions. Now, in general, this course will provide you all word problems. Pharmacy Calculations is all about word problems. So you'll need to be able to read and interpret the problem, extract out the information you need, and then formulate how to solve it. Go about solving it without any computational errors. So that's what we'll do really throughout this course. I really like this slide because it helps you kind of visualize how you're going to proceed solving the questions in this course. There are 4 C's to pharmacy calculations, and they rank from the first C, compute, which is the easiest, to the most difficult to really master at the end, which is critically evaluate. So let's go through these one at a time just to make sure you have a strong foundation on how to proceed. So the first C is compute. And it is the most straightforward of all of them. It's simply being able to use your calculator to accurately perform the calculations of adding, subtracting, multiplying, dividing, using fractions and decimal points as well as percentages. So nothing new, but you must be able to do these calculations reliably and repeatedly using your calculator such that you don't make mistakes. Many of the mistakes on my exams still simply are the result of students not performing the number input on their calculators correctly. They'll mess up by a decimal point, or they might have accidentally hit the multiply when they meant to divide. So simply being able to accurately compute is the fundamental, most important thing you must be able to do. The second C is to convert. This is dealing with the fact that many of the problems that you'll be given will provide you values in one of several different measuring systems. Primarily, we'll be dealing with the metric system. So that means we'll be giving you weight in grams, volume in liters, and length in meters. Okay, but even within the metric system, you need to be able to convert correctly from grams to milligrams to micrograms. I cannot tell you how many mistakes are made on my exams by incorrectly converting micrograms to milligrams, for example, by dividing by 100 instead of 1,000. So knowing how to go between the different measurements within the same system is important. On top of that, many times prescriptions will provide values in an older apothecary system. So we'll give you fluid ounces or drams or grains, and you have to use conversion factors to go from the apothecary system to the metric system. Likewise, patients are often told to use a teaspoonful or a tablespoonful of liquid. So being able to convert that to a volume in the metric system, usually in milliliters, is important. So I will provide you conversion factors so you don't have to memorize them, but it is the ability to correctly convert from one system to the other system, or very often within the same metric system, that becomes crucial. The third C is to conceptualize, and this is the most difficult. This is where we're going to spend most of our time in this course helping you, is to be able to take this word problem, read through it, and extract out the information that you need to know. So oftentimes you will need to start by rewriting the problem such that you're saying, okay, the body weight was this number of pounds. The dose was so many milligrams per kilogram. The concentration is so many milligrams per milliliter. So you rewrite the information that you have. You extract what you have. And by knowing what you have, you can then formulate a procedure for solving for what you need to know. So this is what we need. So let's use what I have to determine what I need to know. So that whole idea of conceptualizing and setting up the problem then relies on your ability to convert and compute to come up with the final answer. So conceptualize is really the hallmark for this course. The last C is to be able to critically evaluate. And to be honest with you, this is the most difficult for students to develop into. It takes time. What we're talking about is after you conceptualize and you then convert and compute and come to your final answer, the question is that a reasonable answer? Is that the kind of answer or the kind of value I should expect for what I have done? That takes time. That's why I give you many problems to solve over and over again. And it's by doing multiple problems and being exposed to these calculations over time that you start to realize what a normal dose for most drugs in milligrams would be, or what most patients' body surface areas range given their height and their weight. It's developing a feel for whether or not the math that you have done produced a value that's reasonable for what you were solving for. And again, this is something that doesn't come at first, but with repetition and with taking a moment at the end to step back and say, okay, does that volume seem reasonable? Is that something a patient could consume? Is this something I would expect given similar types of calculations I've performed in the past? So with experience comes the ability to critically evaluate. It's an important step to do at the end, but is one that will probably take you the longest to really be able to develop. This slide is my attempt to help you visualize the idea of conceptualizing or visualizing a problem. So if we look on the left-hand side, you can see a prescription where it is written that a drug has been prescribed at a dose of 100 milligrams per kilogram per day, and the patient weighs 69.5 kilograms. What is the daily dose? Simple question, but you can see the question. What's below that is writing out what we know. What are the units of measurements? It's milligram. What is the dose? What is the patient's weight? So extracting out what you have from the word problem is the first step, and that's kind of shown there on the prescription. Then really visualizing, what does dose mean? The dose is the amount of the drug, the weight of the drug to give, but that amount is per kilogram of the patient. So we have a dosing amount for the drug, and then we also have a patient here who's visualized, and we know that that patient's weight is 69.5 kilograms. So we can use our dimensional analysis that we'll talk about, set those numbers up, and solve for what we want was the weight of the drug per day. So, straightforward, but it's this idea of being able to take a written question, being able to visualize it, set out the information you need, then line it up using dimensional analysis, and solve for the correct final answer. That's what we will be doing with many of our questions this semester. One of our overall healthcare goals is to avoid medication errors for patients. Pharmacy calculations is a common, unfortunately, source of these types of errors. I show you some information taken from a nursing journal published January of 2022, so a recent publication entitled Medication Dose Calculation Errors and Other Numeracy Mishaps in Hospitals. Okay, this shows and summarizes some of the math-related mistakes that led to medication errors in their hospital. So, and again, I've highlighted a couple of them. I won't read all of them, but remember how I said simply 10 and 100-fold errors, decimal errors. 10 milligrams was given instead of 1 milligrams. That's a 10-fold error of a very dangerous drug. The second one down, in trying to calculate a body surface area, they exchanged the patient's height and the weight was switched in the formula. So they had the formula, but they calculated it wrong by putting the numbers in wrong. Okay? Many drugs are dosed per weight. So 1,000 units of heparin per kilogram is not the same as just giving 1,000 units. It's 1,000 units per kilogram. So omitting the patient's weight can lead to medication errors. A big one, and I highlighted this, is the proportion dose calculation error. This is a common source because this is easy to confuse. So drugs have concentrations and they have units. It also brings up the convert idea. This was example I give here is naloxone. Concentration was 40 micrograms per milliliter. And so essentially you can see there that a mistake was made in using that concentration. Okay, and lastly, just mental dose calculation errors. I mean, using the number of 0.3 times 100, they ended up with 130. They kind of added instead of multiplied. So remember, in this class, you can use a calculator, but you need to be able to correctly calculate. And sometimes you need to be careful with some of the assumptions we make when we try to do some of the mental math. All right, our first real topic for this lecture is the International System of Units, or SI, which was formerly known as the metric system. Unfortunately, I'm old and I still refer to it as the metric system, but in the metric system, when I say metric system, we are using SI units, which are essentially the same and has now been standardized, called the International System of Units, SI, or the metric system. So, and we're going to go through this quickly, but it's important at this stage to remind you that the metric system, or the SI units, are the standard of practice for pharmacy. So all of your calculations, all of your documentation, when we do compounding, all of your compounding records will use amounts, weights, volumes, and lengths expressed in the metric system using some form of grams, liters, and meters. So the SI system is the standard for expressing values within pharmacy practice. Having said that, I expect you coming into this course with some experience with the metric system. This reminds you of the prefixes and their values. Remember that the standard values are grams, liters, and meters, and you can go from those standard values either increasing those by a factor of 10 multiple times, again going from deca to hecto to kilo, going up, or you can go down from that. That is, from a grams, you can go less than by a factor of 10. So you can go down to deci, centi, and milli. And again, I think you know all of that. This reminds you of some of those units. I will tell you, in pharmacy and what normal drugs are dosed at, we are usually smaller values. So again, from the grams or milliliters, we tend to go down to centimeters in length, or milliliters, micrograms. We tend to do smaller. Sometimes when we're measuring bulk amount of drug quantities, we may go up to kilograms, but I've never really seen values in typical pharmacy practice expressed anything greater than a kilo something, and oftentimes you're either at the liters, for example, down to deciliters, centiliters, milliliters. So usually on the smaller end of the scale for some of the metric values. This slide reminds you how to numerically convert between units within the same system. So within the metric system, if we look at converting metric lengths, if we start with the standard of a meter, if we want to go from a meter to a kilometer, which is larger, you essentially have to divide. So if you look at the blue arrows, to go up, you divide by values to go up. But when you start at a higher value, so again, if we start at meters and we want to go the opposite direction to centimeters, then we multiply by the number of fold increase. And again, there's a twofold increase for centimeters. So we would multiply our meters times 100 to express it as a centimeter. But to go from centimeter to millimeter is only a tenfold increase, so we would just multiply that by 10. But if we're in a millimeter and we want to go all the way back to meters, then we would have to divide the value by 1,000. So, and again, you can see that same process expressed by both length in meters and weight in grams and volume in liters. So this process is one that I think you're well aware of, but I'll warn you now, it is one of the most common sources of mistakes. It's easy to make a mental math error here. So it is important to write this out using dimensional analysis so that you can see that you are, in fact, converting. Remember, one of our C's was convert. It is a fundamental skill to make sure that you can do correctly. All right, our first problem involves you trying to, so get your calculators out. I want you to be able to practice your metric conversions. All right, so simple question that asks you to add the following. So we're in weight here. So I want to add 0.5 kilograms to 50 milligrams to 2.5 decagrams and add those together, but express the final total in units of just grams. All right, I show you all of my work here on how to solve this question. So I also provided on the right-hand side the conversions between the different levels within the metric system. So let's start with the first value, which was 0.5 kilograms. So I set that up, and I need to multiply that by a conversion factor. I need to convert from kilograms to grams. So I go to that table, and I can see that from grams, kilo is greater than, meaning by a factor of 1,000. 10 to the third is 1,000. So there are 1,000 grams for 1 kilogram. Okay, so to go up, you need to multiply grams by 1,000 to get to a kilogram. So the conversion factor would be 1,000 grams on top over 1 kilogram, so that the units of kilogram cancel using my dimensional analysis here. So that 0.5 times 1,000 gives me 500, and the final units are grams. Okay, let's do the rest for the remaining. We have 50 milligrams. So I go to figure out my conversion factor from the table. I can see that milli is less than a gram by 10 to the minus 3, which again is 1,000, but it's 1,000 times smaller. That means there's 1,000 milligrams to equal 1 gram. So that's my conversion factor. So I'll multiply by 1 gram over 1,000 milligrams. So multiply that by 50, and I get 0.05 grams at the end, since milligrams cancel. Lastly, let's do the 2.5 decagrams. We'll go to the conversion table, and we see that deca is greater than grams by a factor of 1, or 10. So it's a 10-fold increase, meaning there would be 10 grams to get up to just 1 decagram. So let's multiply 2.5 decagrams by the 10 grams per 1 decagram. So decagrams cancel. 2.5 times 10 is 25. So the final answer would be simply the sum of all three of those. So I'll take my 500 grams plus my 0.05 grams plus 25 grams, and the final answer for this question would be 525.05 grams. The next key concept to discuss is that of concentration. Now, concentration is a ratio. It's the amount of an ingredient per an amount of product. And those two things are different. Ingredient and product aren't necessarily the same thing. So if we think of a liquid product, for example, then we can have a certain weight of drug, so many milligrams of this drug, per so many milliliters. So, for example, 10 milligrams of drug may be contained within 5 milliliters. 10 milligrams per 5 milliliters would be 2 milligrams per milliliter if you divided it out. But 2 milligrams per milliliter is a concentration. It's an expression. It's a ratio of the amount of drug per the amount of the product. All right? So concentration, on this formula you can see, is equal to dose divided by volume. Now, this is a little simplified. In Chapter 6, we'll even spend more time on concentration, because concentration can sometimes be expressed of the weight of the drug per the weight of the product, which could be a dry powder. So it could be a weight per weight. Or in my example I gave you the weight of the drug per a volume, so many milliliters. So that's weight per volume. Alcohols are often expressed as a percent of the volume of alcohol in the volume of the final product. So again, it can be made more complicated. But let's save that detailed discussion for Chapter 6. But let's get back to, let's perform some basic calculations, because this idea of concentration is equal to dose over volume. We can re-express that, because some of our questions, we're going to want to determine a final volume. Well, you can see, we know from the concentration formula, if we rearrange that a volume would equal a dose divided by the concentration. Likewise, if we want to know the dose of a drug we get, then we would take the volume that we are using times its concentration. That gives us the dose. So rearranging that one formula in multiple ways is a common way to solve many problems in this pharmacy calculations class. I wanted to illustrate how important this idea of visualizing and conceptualizing what a concentration really means when it comes to drug dosing by using morphine. Because as you remember from the previous slide, morphine is one of the most commonly found drugs involved with medication errors because it is such a strong pain analgesic medication that even small dosing errors can lead to significant patient injury. So, morphine sulfate comes as oral solutions. You can see here it comes in this concentrated solution. But look on the drug label. You can see this concentration expressed two ways. 100 milligrams per 5 mLs, that is the weight of the drug, 100 milligrams, is contained in every 5 milliliters of this liquid. Or you can go ahead and divide that out. 100 divided by 5 is 20, so that's really expressing it also as 20 milligrams per milliliter. So not many products give both, but you can see the two different numbers and could cause confusion. More importantly, and more what has often led to injury, is a confusion between what is the difference between the milligram versus the milliliter. Okay, oftentimes patients are ordered the amount of morphine in milligrams, but the nurses or the people who input this may assume that's the same as the milliliter value. So if they want 100 milligrams, they may put in the order as 100 milliliters. Clearly, that's going to cause a huge dosing error. So let's use an example on the next slide to kind of use morphine as an example of some of the mistakes that have occurred because of misunderstanding how to compute using concentration. So let's describe a real-life problem that occurred. In this case, a patient was prescribed a dose of 5 milligrams of a 20 milligram per milliliter morphine sulfate concentrated solution, but was mistakenly administered 5 milliliters. So what was dosed was 5 milligrams, but what was given was 5 milliliters. Okay, we have weight and dose versus volume in milliliters. Okay. So let's see. First question for you would be, can you calculate what dose of morphine sulfate was received? So how many milligrams of morphine sulfate did the patient actually receive when they were administered 5 milliliters? Okay. Well, how would you solve that? Well, what we know is the volume was 5 milliliters. What we're solving for was dose. The other thing that we know is concentration. The concentration is 20 milligrams per milliliter. Okay? And to bring that all together, to take what we know, which is the volume and the concentration, what we're solving for is dose. So we use the formula that dose, that we on the previous slide, so one of the versions of the concentration formula that we'll learn is that dose is equal to volume times concentration. We know the volume was 5 milliliters. So we multiply that by the concentration of 20 milligrams per milliliter, so that milliliters cancel. 5 times 20 is 100 milligrams. So what they received was 100 milligrams. I'll remind you what they wanted was 5 milligrams. So if you take 100 divided by 5, that shows it's a 20-fold overdose. They got 20 times the amount that was intended. So question 2 reverses that and says, okay, go back and do what should have been done the first time. What volume should be administered to give somebody a dose of 5 milligrams? Well, again, we know the dose we want is 5 milligrams. We know the concentration is 20 milligrams per milliliter. So now let's use the version of the concentration formula that says that volume here is equal to dose over concentration. I know my dose is 5 milligrams, and if I divide that by the concentration of 20 milligrams per milliliter, milligrams cancel, and my final value of 5 divided by 20, which is 0.25, would have the units of milliliters. So in this example, the patient should have been administered 0.25 milliliters. That volume would have provided a 5 milligram dose. The next subject to discuss is using conversion factors to go from household dosing units to metric units. And I just like this little image here because it kind of shows a lot of the different types of household measurements that you might need to convert from. So, for example, in dry weights, there are ounces that are given. So ounces need to be converted to grams. Unfortunately, and I think confusingly, ounces are also a measure of liquid. They're called fluid ounces, but you can have fluid ounces, or you can have groupings of ounces, can make pints and quarts and gallons. So all of those liquid conversions might need to be converted from those household measurements to milliliters or liters in some examples. Also, the example before of teaspoons. What is a teaspoon? You can see here a teaspoon is equal to 5 milliliters. A tablespoon is 15 milliliters. There are also times we need to convert from degrees Fahrenheit to degrees Celsius. So, and again, this is just an example of the types of conversions that you might need to use to go from a household or apothecary measurements to the metric system. I think the best way to illustrate the dangers of using household dosing, especially for liquids for kids, is summarized in this quote that tens of thousands of kids wind up in emergency rooms after unintentional medication overdoses, often due to badly labeled containers and unclear directions, and not having an appropriate dosing syringe. Using a teaspoon and a tablespoon to actually measure a volume is a terrible idea. We should always be dispensing oral syringes like the one pictured here on the right. The advantage of this sort of oral syringe is the syringe is obviously much more accurate in measuring volume than a teaspoon or tablespoon would be. But it also gives both a volume in milliliters on the left and the household measurements of teaspoons and tablespoons full potentially on the right. So a patient could use the same syringe and measure it either way. We will teach you in lab to always use metric volumes, and if you want to include the teaspoon or tablespoon in parentheses, if the prescriber indicated it that way, that's fine, but the patient should always have clearly indicated how many milliliters of a liquid to administer and provided a measuring device that can accurately measure that to prevent these sort of unnecessary medication errors and injuries. To that end, and I'll just say now that as we go forward in my slides, and I want to introduce this to you, to prevent medication errors for patients reading and measuring volumes, we need to be careful with the zeros and decimal points. All right. We would never want to label a volume for somebody to take as 0.5 milliliters, because if the person doesn't see the decimal point, then they will see it as 5 milliliters, and this has happened repeatedly. So any value less than 1, meaning a fraction less than 1, needs to start with a 0. So you would always want to type on your label 0.5 milliliters. That 0 is a good indicator that the value is less than 1. Weirdly, or conversely, the opposite has occurred. That is when we do too precise. So 5 milliliters should never be expressed as 5.0. That level of precision isn't necessary for a patient. And once again, this has happened when they don't see the decimal point. For example, 5.0 ends up as 50. So again, we never do 0.0 at the end of a number just to avoid these types of medication errors that can occur with liquids. Again, let's do another real-life example of these types of errors that have occurred. So here we have a parent accidentally giving their 22-month-old child a teaspoonful of ibuprofen drops. Now, these drops have a concentration of 50 milligrams per 1.25 milliliters. And you can kind of see that in the box picture I gave you there. Now, the correct dose for their child was supposed to be 160 milligrams. So my first question to you is, how many milligrams of ibuprofen were accidentally or mistakenly given to the child? When they gave them a teaspoonful, how many milligrams did they actually receive? Okay. So in this case, we know the volume they were given was a teaspoonful. We know the concentration. So let's solve for the dose, because we then know that the dose is equal to the volume times the concentration. Now, what we're throwing in here is a conversion. We have to convert our units. So let's start with 1 teaspoonful. But before we get to concentration, we're going to have to convert units. So let's convert 1 teaspoonful to milliliters by multiplying by the fact that there are 5 milliliters per teaspoonful. Teaspoonful units cancel, and we're in milliliters. Okay, 5 milliliters. Now we can multiply times the concentration, expressed so that we have the amount or the weight of the drug on top, 50 milligrams, over the volume of 1.25 milliliters. That way milliliters cancel, and 5 times 50 divided by 1.25 tells you that the final value is 200 milligrams. So the child was supposed to get got 200 milligrams when the intended dose was only 160 milligrams. So they did overdose by giving their child 5 milliliters or a teaspoonful. So the second question is, well, if they wanted 160 milligrams, what volume should have been administered? So again, now we know the dose of 160 milligrams. We know the concentration. So what we're solving for is volume. And we know that volume is equal to dose divided by concentration. So let's take, and using my dimensional analysis, I'll take the 160 milligrams and multiply by the concentration expressed as 1.25 milliliters over 50 milligrams. That way the units of milligrams cancel. Essentially, I'm dividing by the concentration this way. And it is, by doing that math, you can see that the final value is 4 milliliters. So to get 160 milligrams, the child should have consumed 4 milliliters of this medicine. All right, let's do another example. In this problem, a pre-filled syringe contains 20 milligrams of drug in a 2 milliliters of solution. That's our concentration. How many micrograms of drug would be administered by an injection of 0.5 milliliters of the solution? Okay, so what do we know and what are we solving for? We know the concentration. We said it was 20 milligrams of drug per 2 milliliters of solution. So that's my drug concentration. I also know the volume. I'm going to be injecting 0.5 milliliters. So this goes back to that equation where I'm solving for dose. I want to know how much drug. So I want to know the dose. I said dose was simply equal to the volume times the concentration. Okay, so that's what I'm solving for. So let's solve for the drug dose. Well, let's take the volume of 0.5 milliliters times the concentration, such that it's expressed as 20 milligrams over 2 milliliters, so that milliliters cancel. So 0.5 times 20 divided by 2 equals 5. And the units would be milligrams, so 5 milligrams. And many students on an exam would answer it as 5 milligrams. But that's not the right answer to this question, because this question asks for how many micrograms of the drug. So our final step needs to be to convert our 5 milligrams to how many micrograms that represents. So let's start with 5 milligrams, multiplied by the conversion factor. We can go back and look at how many fact that micrograms are essentially 1,000 times less than a milligram. Well, it's less than a milligram by 1,000. It's less than a gram by 1,000,000. But so since we're converting milligrams, we're starting with milligrams. So let's take 5 milligrams times 1,000 micrograms for every 1 milligram. So milligrams cancel, and so 5 times 1,000 is 5,000. So the final answer to this question would be to express the dose as 5,000 micrograms. The next concept to review is this idea of ratio versus a proportion. And this is some basic math, and I'm not going to teach this to you like it's new, but let's just redefine some of the terms. A ratio is the relative amount of two different quantities. The ratio in this example of A to B. We express that as A over B. So a single fraction like that is a ratio. A proportion is simply the relationship of two ratios. So you have a fraction on the left side, A over B, is equal to some other ratio, for example, C over D. Then the two ratios compared to each other are a proportion. Okay? And so, and I'm going to give you some examples here in a minute. So this is some basic thing, but I want you to realize that A over B equals C over D. Let's just look at the left-hand side. A over B. That ratio, if regardless of what C divided by D is, we can say that's a constant. If that stays the same, then without changing the constant, you can see that as A increases, B would increase. Okay, so that is called proportional. A is proportional or directly proportional to B, meaning that as A increases, B has to increase. In this example of A over B equals C over D. Okay. So there is directly proportional and there is inversely proportional. In the example I gave you here, A is inversely proportional to D, because if we say that essentially B times C is some constant, then A is equal to that constant divided by D. Therefore, as A increases, D would have to decrease to get the same constant. So that probably didn't make a whole lot of sense. I think it's more helpful, though, and what I'm trying to get at here is to remind you about proportionality. Direct proportionality, as one thing increases, another thing has to increase. Directly proportional, or inversely proportional. When one thing is increased, another thing will decrease because they are inversely proportional. So let's give some specific examples to make sure you remember these concepts. All right, I'm going to try to use this slide to illustrate for you the idea of directly proportional. A is proportional to B, meaning as A increases, B increases. Now, let's use some pharmacy-specific examples. So this should make sense, and these should be obvious, I hope. Think about the cost of a drug. A patient wants to know, how much is this prescription going to cost? Okay. Well, typically, that's determined by the cost per tablet. And so in that sense, that's a constant. We're going to say this drug has $5 per tablet, or whatever number of dollars per tablet. It has a cost per tablet. That's what's constant. So that's why some prescriptions will cost more depending on the number of tablets. So the total cost is actually going to be the constant of the cost per tablets times the number of tablets. 90 tablets obviously is going to cost more than 30 tablets. So we can say that the total cost is directly proportional to the number of tablets. As you buy more tablets, the total cost will go up so long as the cost per tablet doesn't change. And that's a constant in this example. All right, let's see. Another easy example of this direct proportionality is drug dosing, because often most drugs, not all, but many drugs, are dosed off of patient weight. Okay, and we know that because the dosing instructions from the manufacturer for that drug say that you should give so many, whatever number, milligrams per kilogram, whatever the units are, but it's an amount of drug per kilogram, based off of the weight expressed in kilograms. And that's the same for everybody, okay? The milligrams per kilogram, or the amount per drug per kilogram, doesn't change. What can change is the patient's weight. Obviously, different patients weigh different amounts. So the total dose, which is equal to the weight times this constant of the drug milligrams per kilogram, we can say that the total dose is directly proportional to the weight. The more the patient weighs, the greater the total dose. The less the patient weighs, the smaller the dose they'll get, because the amount per kilogram is a constant. So those are examples, some just simple pharmacy examples of things that can be considered directly proportional. Now let's give some examples of things that are inversely proportional. That is, as one thing increases, this other thing will decrease because they are inversely proportional. And let's just use the formula that we've been using for concentration. That we said that concentration is equal to an amount of drug divided by the volume. Okay, in a liquid sense. Okay, concentration is drug weight over total volume. Concentration is amount over volume. What in this example is, it says for a constant amount of drug in the solution. So if we don't add any more drug, if the amount of drug, it doesn't change, but we increase the volume, if we dilute and add more water to the same amount of drug, the concentration will not stay the same. The amount of the drug in this case is the constant. What's changing is the volume. And as volume increases, then concentration decreases. It's inversely proportional. So if the amount of drug doesn't change, but the volume increases, to get that same constant, you have to have a decrease in the concentration. So concentration and volume are inversely proportional. Another example that I can always visualize, I just remember from chemistry, was the ideal gas constant. So, or the formula that says pressure times volume equals nRT, if you will. So you can arrange that and say that the pressure is equal to nR times T, or temperature, divided by volume. And that's why they always would say in these questions, I remember in high school, at a constant temperature. So if the temperature doesn't change, it's temperature that's a constant, then nR, which are constants as well, that's going to be our constant. nRT is constant, which means that pressure is equal to that constant over volume, which means that as you increase pressure, the volume of the gas has to decrease to get that same value, because pressure times volume equals a constant. So if pressure increases, volume decreases. If you decrease the pressure, then the volume increases. It just reminds you that in some of these formulas that we're going to use, you're going to have some units that are directly proportional to each other, and in this example, some that are inversely proportional. Let's work a problem describing and showing a proportional relationship. So in this problem, it reads, if 3 tablets of aspirin contain 975 milligrams, how many milligrams of aspirin are contained in 12 tablets? Okay, so what do we know? We know a relationship. It's not really a concentration, but we know a relationship that 3 tablets contain 975 milligrams. So we do have a relationship there, a ratio, if you will. We also know that we want to know how many milligrams are contained in 12 tablets. So our number of tablets are 12 tablets. So let's set this up as a proportion. So the first ratio that we know is that for every 3 tablets, and I'm going to set that on top, over 975 milligrams. So 3 tablets over 975 milligrams, that's my first ratio. Let's set that equal to set up a proportion. And in this case, look at the units. We have tablets over milligram. So let's set the number of tablets that we're interested in this case 12 tablets. So we put 12 tablets on top over some unknown or X milligrams. And what we're solving for is the milligrams of aspirin contained in 12 tablets, because I know in 3 tablets there's 975. So now I'll set that equal to 12 over X. Okay, so this is an example of our proportion. We have 2 ratios equal to each other, and by doing that now we can solve for an unknown. Since we only have one unknown, which is the actual amount of aspirin in the 12 tablets, we can solve for that. And you can certainly do that more than one way. So I show my work here where I cross-multiplied and got 3 tablets times X milligrams equal to 975 milligrams times 12 tablets. Then I divide each side by 3 tablets so that I just have X milligrams on the left. So essentially, if I take 975 times 12 divided by 3, and you can see where the units of tablets cancel, my final units will be in milligram, and my final value is 3,900 milligrams. So 12 tablets contain 3,900 milligrams, but we used a proportion to be able to solve that. This slide shows an alternative approach to solving that same question. And remember, we were giving you the A's over B's equals constants. Well, essentially, we have a ratio of tablets to the weight of aspirin in them that we can think of as a constant. So what we could do is set up and determine this constant by saying that I have 975 milligrams for every 3 tablets. That's that same ratio we talked about before. So I have a ratio of weight per tablet, 975 milligrams over 3 tablets. Well, let's go ahead and divide that out. And again, so the 3 will go into the 975, and so 975 divided by 3 is 325. So 325 is our number, but now remember, our units don't cancel. We have milligrams over tablets. So our units of this is what's a little tricky for some people when you divide that. It's 325 milligrams per tablet, but that is our constant. Now we can use this as a constant by multiplying by the number of tablets. Since we know there's 325 milligrams per tablet, and we have 12 tablets, 12 tablets times that, tablets cancel, 12 times 3 is 3,900 milligrams. So you could either set it up like we did in the first example as a proportion with 2 ratios, or you can use the 1 ratio, numerically combine them, and then use that times the number of tablets. Both give you the same answer, and both are just 2 different ways of solving the same sort of directly proportional problem. The last topic for this lecture is about dimensional analysis. And I've already mentioned myself doing this a couple of times throughout this lecture, and it is the way that I strongly recommend you set up your pharmacy calculations. I won't require this, but it is a system that allows you to see what you're doing before you do any of the math. And you can actually verify you're going to get the right answer by making sure that all of your units cancel. By doing this, you can make sure you're multiplying when you're supposed to and dividing when you're supposed to. Otherwise, it's very easy to make the mistake to forget to do that. So in this example, as you can kind of see on the thing, let's convert 2.5 liters to fluid ounces. And like on the exam, I will give you conversion factors like 1 liter equals 1,000 milliliters, or 1 fluid ounce contains 29.57 milliliters. So that's not the trick. The trick is knowing how to multiply or divide the different numbers to get to the right answer. So in this example, we start with the 2.5 liters on the top. And then next to that, we draw a box with a line. And what we're going to do is use our first conversion factor. What we need to convert is liters. The conversion I have is to convert liters to milliliters. So let's use the 1 liter is 1,000 milliliters. But the question is, does the 1,000 milliliters go on the top or the bottom? Well, you know it needs to go on the top because what we need to cancel are the units of liters. So I put 1,000 milliliters on top over 1 liter. Now I can see that I could cross off my liters, and by the time I do 2.5 times 1,000, now my units are milliliters. Okay, but I want to get to fluid ounces, so I have to use my second conversion factor. And now keep in mind, I need to cancel milliliters. So what has to go in the bottom is the number with the milliliters. So I put 1 fluid ounce on top over 29.57 milliliters. That way milliliters units cancel, and my last units will be fluid ounces. So my 2.5 times 1,000, then divided by 29.57 would give me the correct final answer of 84.55 fluid ounces. Okay, so again, using this setup, and before you do any math, write out the whole question and go from the units you're starting with to your final desired answer units, and make sure your units are canceling, whether you're multiplying or dividing, before you do any of the math. And then the last two things I wanted to show at the bottom here is, while I love dimensional analysis, the other things pharmacy students sometimes do because they're trying to do things quickly is to omit writing out the units. Dimensional analysis only works if you write out your units so that you can see your units cancel. So the example below there, you can see where the 80 over the 1 is in red because that was done wrong. The bottom example shows you how you can take a concentration of 400 milligrams per 250 mils, and if you wanted to double it, you're solving for how much of this volume you need to use. So I won't go through the whole formula, but you can see if they had done the units of milliliters over milligram, it would have been 1 over 80 instead of 80 over 1. So the point to using dimensional analysis is you use your units to guide your math, whether you're multiplying or dividing. It avoids errors, but you have to write the units down and step by step make sure that you show that the right units are canceling and that you have the right number in the right place, whether it's the numerator or the denominator. Let me work a couple of examples of this using dimensional analysis in a more complicated example. So in this question, it asks that we have 1 liter of a dextrose solution to be administered over 8 hours. Using an IV administration set that delivers 10 drops per milliliter, how many drops per minute should be delivered to the patient? See, that's kind of a complicated question. There's a lot of moving parts there. I give you the conversion factors shown there, so I won't belabor that. So where do we start? Let's start with what we know. We know that we have a ratio. We know that we have 1 liter of solution that needs to be administered over 8 hours. So you'll notice on the far left, I put 1 liter over 8 hours. That was given to me in the question. That's what I'm starting with. What are the final units? The final thing I want to know is how many drops per minute. So this is just a conversion. As I said, one of the first C's is to convert. A lot of pharmacy calculations are simply to convert from one thing to another thing. I want to convert from liters per hours to drops per minute. Okay? So how do you progress? The one thing that I need that I also know for my infusion set that has a relationship is 10 drops per milliliter. Okay? So in this case, you can do it in other order. Let's convert our volume first. Let's convert volume in the units of liters to a volume in drops, and we can do that. But my conversion is 10 drops per milliliter, so my first step is to convert liters. So I'm going to take my 1 liter over 8 hours times. Let's convert liters to milliliters by multiplying by 1,000 milliliters per liter. My units of liters cancel, and I'm now in milliliters per 8 hours. Okay? We're not done yet, but I'm in milliliters. So my next step is to multiply by the conversion factor I had that said there are 10 drops per milliliter. And I'm going to put 10 drops on top over 1 milliliter because I want my milliliters to cancel. So when I multiply that and then by 10, then my milliliters cancel, and now I'm in drops per hour. And that could be my final answer, but the final question really wants it in drops per minute. So while I've converted my top unit from liters to drops, I now need to convert hours to minutes. So I'm going to multiply then by a relationship. For every 1 hour, there is 60 minutes. And again, I have 60 minutes in the denominator because I need to cancel my hours. And hours is in the denominator at the start, so I needed times 1 hour so that hours on the numerator cancel with hours in the denominator. And what's left are drops per minute. So if you do that math all the way across by taking however you wanted to do that, but you do the math straight across, you would get 21 drops per minute. Let's complete another question. In this problem, we have a 0.5 milliliter of an investigational ophthalmic solution that contains a drug at a concentration of 10, be careful with the units there, it's 10 micrograms per milliliter. And the question asks how many micrograms of drug would be administered in a 50 microliter drop. Okay? And sometimes I will give you multiple choice answers here to try to catch you with common mistakes. So let's see. I'm just going to work it through and see what answer you got. So the first thing is to extract what we know. What we know is that the volume we're going to administer is 50 microliters. Be careful with your units again, microliters there. That's a volume. We also know the drug concentration. It's 10 micrograms per milliliter. All right. And then lastly, we remember that we have a volume and we have a concentration. It wants to know how much drug or how much dose. So we know that dose is equal to the volume times the concentration. All right. The only trick here is the fact that our drug concentration is in micrograms per milliliter, but our volume to administer is in 50 microliters. So we need to keep that in mind. So with using dimensional analysis, though, we can do this all as just a single formula. So let's start with our volume. We're going to take our volume times our concentration. So we start with 50 microliters, but we have to first then convert the microliters to milliliters. So as a reminder, there's 1,000 micro in a milli. So we're going to multiply for every 1 milliliter over 1,000 microliters so that microliters cancel. And now I'm in milliliters. So now I can multiply by my concentration of 10 micrograms per milliliter. Milliliters will cancel, and my final value will be in micrograms. So if you do that math all the way across, your final number would be 0.5 micrograms as the correct answer. And we're ready for our last question, which is a little bit trickier. So let's see how this one reads. It says, in this example, a physician has prescribed 350 milligrams of penicillin V potassium to be taken 4 times a day for 10 days. Okay, that's great. We know what the patient's doing. But the question really wants to know how many milliliters of a suspension containing 125 milligrams of penicillin V potassium per 5 mLs should be dispensed. Oh, so what we're really asking for here is the volume of this liquid to dispense such that the patient has enough to complete what's been prescribed for them. All right, so what do we know? Well, let's say an easy thing to see that we know is we know the drug concentration. We know the concentration is 125 milligrams per 5 mLs. There's my drug concentration. I also know what I'm looking for at the end. I want a volume. I want how many milliliters. So what I want is a volume. And I know that the volume is equal to the dose divided by the concentration. And I just said we know the concentration is 125 per 5. So the tricky part to this question is while we were given the dose, we weren't given the dose expressed like we need to use it. So we have to use the individual parts, the 350 milligrams and the 4 times a day and the 10 days. We have to use all of that to be able to determine the dose to then be able to use in our formula. Okay, so but with the beauty of dimensional analysis, look down below in my work and you can see how this can all be done in one long series of ratios. Okay, and we're going to start to make sure that our units match and cancel all the way across. Okay. So the way I would approach this is the fact with this. The amount of volume they're going to need is dependent on the dose, and the dose is dependent on the number of days. So let's start with the fact that we need enough liquid to last 10 days. Okay, so if I start with 10 days, then how am I going to cancel days? Well, I know that the patient is going to take 4 doses per day. They're taking it 4 times per day, right? So 4 doses per day. So 10 days times 4 doses per day, days cancel, and I now know I need 40 doses. All right? Now I'm in doses. But I want to convert now from doses to the milligrams. If I need 40 doses, how many milligrams need to provide all those doses? Well, I know each dose is 350 milligrams. So if I multiply by 350 milligrams per dose or overdose, then dose cancels, and now 40 times 350 would be the number of milligrams that I need total. So I'm almost there, but I don't want a dose. I want a volume. Okay, so now it says you need to divide by the concentration, but in dimensional analysis, we still multiply. Here's the beauty. What I'm going to multiply by is the concentration expressed however I'm going to need to express it so that my units cancel. And since I need to cancel milligrams, I'm going to multiply by expressing it as in 5 milliliters on top over 125 milligrams. I see my milligrams unit cancel. So the math going all the way over is 10 times 4 times 350, then times 5, then divided by 125. And by doing that and by checking my units all the way across, my final answer will be in milliliters. And doing the math shows me that I would need 560 milliliters of this suspension to provide a 10-day supply. All right. Well, I hope you found this a useful review for some of the basic concepts that we're going to continue to build upon in this class.